So basically leveraging AI in the 6G context to go from intents, so expressions of having something to happen in the world, to actually then getting concrete results. So that is the topic, and my focus will be on IoT systems. And here actually in the presentation, the first slide, you see this hall, and this is the Slush hall several years ago. So Slush is this very big startup event in Helsinki. So we see the University of Helsinki stand there, and this photo from the event is very much about IoT and also AI, and to a certain extent about 5G as well. So here what you can see is that we have these colors at the top of the photo, so in the ceiling. So there we have an air quality station. So this kind of high quality station is hanging from the ceiling. And then in the hall, we have small portable air quality sensing systems that are connected wirelessly. And they all contribute information so that we can build accurate real-time understanding of the air quality and the chemical cocktail in the hall. So that's an IoT application, and I find this kind of a very compelling use case, because we have scientific measurement devices, we have low-cost devices, and we need to combine these to get to the best insight and best knowledge about the environment. And once we have that insight, we can then use that to improve the safety and well-being of people. So that's an example that I will use later on in my talk. But now let's get going. Let's go forward. So a bit about my background. So I come from the Faculty of Science. That's a hub of science and technology in Helsinki, within University of Helsinki. And we cover a lot of ground in natural sciences and technology. And also AI has been a focus area for us for a long time. In Finland, we have a 50-year tradition in machine learning, so we have been contributing to that. And more recently, AI for sciences. AI for science has been a rising trend and a rising theme, and we work very much with that topic. And today's talk is about a kind of a narrow part of this AI for science. So we focus on AI and 6G. Also in the background, we have 6G Finland. That's a network supporting collaborations in the 6G area. So facilitating sharing of information, best practices, helping to form new consortiums and so on. So 6G Finland is a one-stop shop for 6G related activities in Finland. Then also the work I'm presenting is supported by our funding agency, Business Finland. They have a 6G Bridge program. So the projects and their results that I'm presenting are supported within the 6G Bridge program. And we have 4 key activities. So at the bottom you see 6G TNF. So that's 6G Test Network Finland, building on our 5G network. And that's the essential ingredient for the empirical work that we do in the 6G area. So basically building the radio access network, building the core network, having the deployments, getting real-life understanding, real-life data from the deployments. And on top of that, so we have the ORAN project that explores the opening of the APIs. So the ORAN work, which makes it possible to control elements in the radio access network using APIs, so getting information and also configuring elements. And that's of course very, very important when we want to increase automation in the network. Then on the right hand side you see 6G neural pub sub. So that's also one important ingredient. So I mentioned intents. So when you have an intent, you need to be able to issue that to the network, to the system, and then do something useful with that. So this neural publish subscribe is about giving the intent to receive content, to receive some service. So you describe what you need to happen. And then the system, what we call neural router, then tries to understand that what is the intent, and then delivers content based on the intent. So that in a way doing information routing, but at a much more expressive level than before. And going beyond that, so we would then want to enable also the provision of this software systems of services based on the intent as well. So we're exploring that aspect also in this context. But neural routing we see as an important ingredient for getting to intent-based systems. Then on the left-hand side, you see that we have also an activity on the digital twins. So creating virtual digital replicas, copies of IoT systems, the physical IoT systems. And digital twins are very useful. So we can explore their properties. We can predict, how a system could work. We can simulate and use this information to improve the real-life physical system. So digital and physical work together for the improved end result. And we are envisioning millions of digital twins in the near future for IoT and also, of course, for other cases as well. And we are working on a platform to enable that. So there are many exciting research questions in that area as well. So now going forward, so I mentioned the air quality IoT case with the title slide, and now we kind of return to that case. So we call this project MegaSense, basically combining computer science, atmospheric sciences, geosciences to understand air quality in our environment. And we built many deployments for studying the environment, and we used 5G connected sensors, so low-cost sensors, but also higher quality sensors and even scientific measurement stations to get this versatile information that we can then combine and use when understanding the environment and then predicting properties of the environment. And this activity was very fruitful. We have many scientific contributions in the area, and we learned that, for example, calibration is very, very important. And we can use a calibration hierarchy, so the higher quality devices in calibrating the lower quality devices. And one result was that machine learning based calibration using only 2.5 days of data that was kind of gathered from a collocated deployment was sufficient to boost the accuracy by 56%. So very nice possibilities to how we can use AI to improve the sensing quality and of course then extract insights from the data. But then we also learned quite a lot about the real-life implementation of such scenarios. And that's something that we have been really thinking a lot, that we learned while doing this activity, measuring air quality and analyzing it, that it's not that easy to do large-scale and heterogeneous IoT deployments. There's a lot of work involved. And we then had the question that to what extent can we automate this? And now we get to the intent-based operation. So what if we could just have the intent, that you have the intent to have air quality data and other insight from the city and from a building, and you would be able to formulate this intent. And you would be able to, of course, in the background, have information about the APIs and the sensors already installed and so on. But now, given the intent and then the information we have in the background, that then would serve as the basis for automating this. So we have been exploring this, that can we automate IoT deployments? Can we automate networks using intents? You just describe what you want to happen, and then the system is able to address that. And we don't have this capability today, but perhaps we can have this in the near future. So now we have been going to this intent-based 6G, and of course language models, since they work very well with multimodal content, they understand text, images, and so on. So they are a very useful building block for intent-based systems. Getting to understand the intent and then formulating plans how to implement the intent. So this is what we have been exploring, and we see For LLMs, we see two key areas. So one is task management, so that we are able to have task planning, decompose the intent into sub-tasks, do task execution, collect the responses, iterate, and so on. So task management, so these kinds of agentic capabilities. And then tool management is the second important capability. So being able to choose and dispatch tools, make tools, and then of course use the tools. And when we combine these, so task management and tool management, we have a quite powerful setting for applications for going to this intent-based world. So that has been the starting point in a way for our intent exploration. And we also, within the 6G flagship context, so 6G flagship is one of these national centers of excellence in Finland. We have been then discussing the topic that language models, large language models, and 6G, intent-based operation, and so on. So we then wrote a white paper on this. So the community grew, and then we, through the community, developed a white paper, which is available online. So here you can see that it's large language models in the 6G enabled computing continuum. And if you're interested, please have a look at the white paper. So it covers a lot of the basic considerations here, that how these language models can be useful in the 6G context, how they can act as controllers, and how we can then gradually deploy more and more intent-based operation in the network that then supports applications. And since writing this white paper, we have been then exploring the more concrete research items related to this, and also performed a number of prototypes, and also trying to get real-life understanding that how this all then works, and how the results can be combined as well. In the white paper, we outline a system design which is the following, so that we have the traditional control plane, user plane, and also application logic division. And we see that we would have a new component called AI interconnect that would then be integrated into these logical components, providing help in terms of orchestration and management of the AI components, AI pipelines. And the interconnect would then need to take care of, in a way, selecting the AI models being used, updating those, their placement, so distribution in the network, task coordination, communications related aspects, and also routing related aspects as well. And certainly we need also safeguards and audit trails as well for everything. And the security is a very important consideration. And then this would work across the edge cloud continuum, so that we would have a device front haul, mid haul, back haul, and the core network. So we would have the, in a way, the distributive aspect as well. So that's the AI interconnect that we have been sketching, and partially also we have been experimenting with this. And as a use case example, so now continuing on the IoT use case track, I mentioned air quality, but we can also consider agri-tech applications. So let's say that we have an intent, given our agricultural deployment, that given a new hybrid soil variant, we would want to have a tool that can then assess soil's reaction to various practices, various conditions in our deployment. And we would then issue this intent to our system, and the system would then, the AI interconnect, helping there to then realize the implementation of this intent, so that we go from the intent to actual real life world monitoring and change. And the sequence diagram illustrates that in a very high level, that how this could happen, that we issue the intent, we give a subscription, and then there is tool creation, pipeline creation, data access, many different things happening in the back end, in the background as well. And then we would be able to then have the tools elements, the language model, tasks, and also code generated, so that we can deploy this this intent and then deliver the content, the services, insights to the user. So that's the basic idea that we would want to realize. And now going forward to the projects, to our selected results in this area. So I mentioned this neural router, neural publish subscribe. So we see this as an important enabler so that we would have these endpoints issuing these subscriptions, issuing intents, and the system, so the router would then deliver content following the intent or aligned with the intent. So that would then offload quite a lot of information delivery complexity from the endpoint to the system. So the middleware would take care of this, and we would expect that agents would benefit from this kind of an operation, that agents could then work on a very high level with the intents, and the system would then take care of, in a way, the machinery to deliver what was then subscribed with the intent. So it's a project that we have been working on, and we have been implementing several prototypes of a neural router. And here you see an overview. So basically, it's an element that accepts intents. We see that it works on two different levels. So we have a baseline routing level operating on more simpler intents that more are about information dissemination, so getting the information, maybe doing some aggregation. And then we see that there is a higher neurosymbolic layer and having complex event processing style capabilities and more state that would then be able to help in actually implementing more complicated intents and distribute those in the network. So two levels that work together. So that has been the design, and we have been now, as mentioned, implementing this and experimenting with the router. And of course, this is quite heavy machinery, so this is not replacing Apache Kafka or any of these message queuing solutions, but it's an additional element that brings more capabilities in terms of information processing and dissemination.
Hi, Sasu. Could you please share again your slides? Thanks.
So continuing, so then we have been working on the neural router, and then we have also explored the complex event processing capabilities. And here you see one prototype we implemented based on Kafka, and having these, we have these traffic cameras, having the cameras deliver frames through the Kafka system to an agent system, then doing complex event processing. So that was the basic setting, and we have frames having different complexities. So very simple image frames, or then very complicated and also very fast, changing frames as well. And the plan and the idea here is to really allow intent-based queries over these streams of frames using the agent system, and explore the capabilities that we can gain through language models, and also understand the performance aspects as well. So it's something that we have been then implementing and experimenting with this, and the results indicate that agents are useful in this scenario. So we used AutoGen for the implementation, and the results are encouraging that we can detect many issues from the scenes. The agents can do that. They can transform our intent into operations, and we can get insight. But then certainly there is a latency cost. So the more agents we have working on the data streams, the more time it will take, and the time is measured in seconds. So it's not real-time operation. And we are looking at the optimizations of this system as well. Also, we have been looking at the smart spaces in more detail, also in the case when we have people moving from one smart space to another. So you move and the agent moves with you. Let's say that you have an agent that helps you access the smart space. So we have been looking at how to configure the smart space when these agents come and go. So in a way, taking mobility into account. And here also we see that the interconnect is a very important and a necessary element helping with this configuration aspect. Also, the empirical side is very important. I already mentioned several implementations. We are also working on the testbed angle. So together with Oulu University, we have been developing a joint testbed to explore intent-based systems, to explore agents in the 6G context, building on the test network facilities we have in Finland. And this is of course connected with the Lumi supercomputer, so we can use Lumi for the heavy lifting in terms of computing needs. But the testbed activity is also very active and lively at the moment. So now we also see that building on this PubSub, building on the neural router, building on many of these elements, we can then approach the deployment of digital twins. And we have been then realizing this digital twin platform, very much grounded on publish, subscribe, and also the neural router ideas. And the idea is that we then create digital twins based on IoT device telemetry, so that we can then use the digital twins to understand IoT deployments, explore configuration parameters, explore new features, and so on. And the system has been implemented, and we have also added Gen AI features, so the language models are also integrated with the telemetry digital twins. And this slide illustrates this concept, so that we have on the left-hand side, we have the digital twin stack with the telemetry. We create the digital twin, and then we connect that with the LM language model kind of analysis. And on the right-hand side, we see that we can then issue queries, prompts to the digital twin for getting insights into what is happening with the smart space environment. And we can do descriptive, diagnostic, predictive, and prescriptive analytics using the language models. Now, what is still open is, can we use these insights into control operations? So can we also control the smart space based on these insights? And that's something that we are exploring now, especially with the language models. We have to be very careful that how we then implement any insights to be sure that we don't have any kind of side effects from that, so that everything goes well. Also for digital twins, so we have been looking at adaptive twinning, so how to synchronize the physical systems, so in a way the real life part of the twin and then the digital part. How do we do the synchronization? And there is a reinforcement learning agent developed for this, and the results are very encouraging, that we can optimize data transmission, we can try to keep the accuracy good enough, high enough, and we are in a way continuing with this track in optimizing these digital twin systems. And this work, so we're very happy, received the IEEE ICDCS Best Student Paper Award this summer. So we're very happy about that result. Also, the local language models are important, so that we could have a local intelligence in a way based on the language models. And we have been looking at how to run these, especially inference operations. And one key consideration is memory. So there are many benchmark results that we have been analyzing, and memory. So both RAM and GPU, and also the context memory, those are really crucial. And we are looking at how to optimize these. Then, so going more into this world of network management. So I mentioned the intents, using intents to generate IoT solutions, but we can also use intents to manage the network. So we have been also exploring this angle, that to what extent we can use small language models and prompts and intents to do network management. And here on this slide, you see that on the left-hand side, we have the LLMs and the agents, and on the right-hand side, we have the network environment. We have the cluster, and then we have failure simulation, we have questions, and we have explored that how small language models, given API access to the cluster, given code generation capability, with and without fine-tuning, how well they perform in network management tasks, especially diagnosing and debugging networks. And the results so far have been also encouraging here, that small models can be effective for specific tasks. There is quite a lot of variance across the models. So some models are really bad, some are good. So it really depends on the model, and then also fine tuning is something that is very non-trivial to do. We actually didn't find fine tuning to work so well with the small language models for this network management case. And certainly real-world data sets are needed. So more work needs to be done to get good data sets that we can use for testing and also for doing the fine-tuning and so on. And this work received the Best Paper Award at AI/ML Systems, so we are also happy about that as well. So now, still thinking about the AI and 6G area. So I believe we have a huge need for upskilling people for the topics. So what is 6G going to be about, and also how AI plays a role here. And at University of Helsinki, we have been focusing on this education, opening that, and we have quite significant, massive open online course activity. You can find the courses at mooc.fi, and one of the success stories here has been Elements of AI course with close to 2 million participants. And as a newer course, we have a MOOC on 6G MOOC that is free and available for everyone. So if you're interested in the education aspect, please have a look at mooc.fi. And now to conclude, so I have been talking about intent-based systems, how we can use language models to enable intent-based operation in the 6G network context, how this can be done for the network itself, for the network management aspect, but also for the application. So taking the intent and then generating the pipelines and system configurations and code to deliver what is really needed. And digital twins play also a role here, both for the network management, but also for the applications as well. And I believe that these are ingredients for understanding how to create real-life intent-based systems. And we are exploring this further and also combining what you have already to create more complex and more elaborate systems for the real-life cases. So that is an ongoing activity. And we are very happy to tell more if you're interested. Thank you very much.